Welcome to the chapter on designing with USB for the msp430. We begin with a quick introduction to what is USB. USB was designed to replace a wide variety of other serial buses, hence the name Universal Serial Bus. It's a master-slave bus architecture where the single host controls every transaction on the bus. Using hubs, USB can support up to 127 different devices. Each device is identified by a unique vendor and product ID, which are also called VID and PID. The host keeps track of everyone on the bus, while the devices only see the host. To them, it appears to be a single point-to-point bus connection. The USB protocol has gone through a number of revisions. USB 1.1 was released back in 1995. This version provided separate host and device connectors, along with supporting two different speeds. Low speed at up to 1.5 megabits per second, while full speed had data rates up to 12 megabits per second. In 2000, the USB standard was upgraded to 2.0. Along with the low and full speeds, a much faster high 480 megabit per second rate was added. Other major additions to the standard included a power supply of 500 milliamps provided on the USB cable. In 2008, USB added the 3.0 revision, once again backward compatible to USB 1.1 and USB 2.0. The new revision, though, added a super 4.8 gigabit per second rate, as well as a bump up to 900 milliamps in source power from the USB cable. While these are great advantages, it's overkill for many systems where low power and cost are primary directives. The msp430's USB port supports the USB 2.0 standard, but only operating at the full rate. Seeing that the fastest msp430 devices only run up to 25 MHz, it's not hard to wonder why they can't support the high rate. Additionally, the msp430 only provides device support. If, by the way, you needed host or on-the-go support, you might want to check out TI's Tiva-C line of ARM Cortex M4F processors. As shown here, the USB cable provides 4 different signals. Of the first two, one is the power signal, called VBus, and is a plus 5 volt supply, and the other provides ground. Not only does this pair provide USB 2.0 devices with up to 500 milliamps of power, but bringing the signal high is how the host begins communicating to a device. We'll see more about this later in the chapter. The other pair of signals, D+ and D-, provide a differential data signal from the host to the device. As most hardware engineers know, using differential signaling provides more robust data transmissions. Finally, the USB standard supports hot swappable devices. This means they can be connected and disconnected as needed. Therefore, your USB application should remain flexible. By this, we mean that your application needs to be written so that it can handle an asynchronous change in the USB connection state. This might include your host putting your device into suspend mode, where you'll receive a reduced power supply, or the end user disconnecting your device from the host by yanking the cable. As we stated 2 slides ago, the msp430 is a certified USB module that supports 1. The USB 2.0 standard, 2. Operating at the full speed rate, and 3. In device mode only. That said, there are some other nice features provided by the msp430's USB port. For example, both the transceiver, that is the PHY, and the required pull-up resistor, PUR, have been included. Also, the port includes its own LDO voltage regulator, so it can run directly off the power from the USB cable. Further, the USB power can be used to source power for the entire processor. We've also included a PLL that can provide the precise timing required by the USB standard. Oh, and the USB stack takes care of setting all this up for you using the external XT2 crystal. Make sure you check out the TI msp430 USB page, and while you're at it, you may want to look up some of the other USB products from TI. If you're new to USB, here's a few good references to get you started. We found them useful when we were learning how to build USB interfaces. And now, here's a quick introduction to the msp430 USB stack. The msp430 team has done a great job putting together their USB stack and tools. All of these are found in the USB Developers package that's a part of msp430ware. Taking a quick peek at it, here are some of the highlights as pointed out by the red arrows on this slide. To begin with, they've provided an excellent USB programmer's guide. The descriptor tool is truly unique. It makes easy work of the tedious and error-prone job of creating USB interface descriptors. The USB HID demo is a host-side tool that lets you interact with custom devices implementing the Human Interface Device class. It's like a serial terminal program for HID devices. Finally, the rich set of examples provided by TI not only give you a way to play with USB, they also make excellent starting points for your own applications. We recommend that most users start out with either one of the many examples provided with the developer's package or the empty USB project example. Let's take a quick peek at the empty project. Can we really call this an empty project? The msp430 apps team has already included all of the pieces we need for a USB software design. From the top, the driver library in gray has already been included for us. Likewise, the USB stack is already there too in a folder called USB_API. We've used the blue background here to show that you shouldn't need to edit these files. USB app folder has a number of pre-written functions for you to use, as well as change if you'd like to. These are functions like CDC, send data in background. Also, there are a number of callback events in this folder that we can fill in as needed. We use pink here to indicate that you might want to tweak this code. Don't worry, we'll talk a little bit more about these events and these functions later on in the chapter. Moving down again, we see the USB config folder. This starts out empty, but when you run the descriptor tool, this is where its output goes. We don't have to manually edit the files in here, so we colored it blue. Finally, they've provided us with a starter template for main. This provides us with a good USB framework to build upon. As shown here from Wikipedia, there are a great number of interface classes supported by the USB implementers forum. Some of these are quite common, like keyboards. Others are on the esoteric side. The msp430 team has selected a few of these that fit within its low-power, low-cost DNA. Thus, our USB stack supports 1. Communication device class, that's known as CDC. This is things like virtual COM ports. 2. Human interface devices, known as HID, things like keyboards and mice, as well as a simple, easy data pipe serial port transactions that you can do over HID. And 3. The memory storage class, known as MSC. This is, well, like USB sticks, although you're more likely to use this to share preference or log files between your application and the host. We also support a class called PHDC, but this isn't widely used. By the way, this slide gives us our first peek at the msp430 USB descriptor tool. This GUI greatly simplifies the tedious part of USB development. So, what is the descriptor tool all about? Basically, every USB interface has to be described by a large group of data structures. Only the USB standard doesn't call them that. Rather, they call these data structures descriptors. Looking at this diagram, we get a brief glimpse at the many layers of descriptors that are needed. We need one for the device, then one is needed to describe the configuration. Drilling down further, each interface needs its own descriptor too. And while it doesn't end there, I'm sure you're starting to get the picture of the layers of descriptors needed for one USB device. The descriptor tool creates all of the needed data structures, that is, descriptors, for our custom USB device. Each time you click a big blue button, such as CDC, that interface is added to the description. All you have to do is fill in a couple of parameters in the dialog. And then, when you push the Write Code button, the descriptor tool drops all of the results into the USB config folder in your project. By the way, have you ever had Windows ask you for an INF file before? That's basically a descriptor for the host side of a USB connection. Bully for the descriptor. That tool even makes the INF files for you. Okay, so by now, we should know what the driver library is all about. If not, please refer back to Chapter 3. And we just looked at the descriptor tool, so we've checked off the USB config folder. Let's take a peek at what functions are in the USB stacks folder. That is, the USB_API folder. While the USB stack handles many of the underlying issues for us, we're going to focus on the user's API. That is, the calls that we might make from our program. The first part of this includes the functions that are generic to USB interfaces, such as starting, stopping, enabling, and disabling the USB port. Next, we can see that the USB stack has a set of send and receive functions that are specific to each supported USB class. Okay, that was a quick description of the USB stack API. Now let's turn our attention to the USB app files included in the empty project. As we can see, these functions are technically part of the application layer, as opposed to being in the USB stack itself. These app-level transmit and receive functions were provided by the msp430 apps team to help us implement our program's code. I like to think of them as wrapper functions. They directly build upon the class-specific API, making it easier to do what I want to do. For example, rather than using just the class-specific sendData function, they provided two variations for me: sendData and wait until done, or sendData in the background. If you find you've got something specific that you need for one of the classes, just grab their wrapper functions and tweak away. The other functions provided in the USB app folder are a set of event handlers. If it makes more sense to you, you can think of them as callback function. The apps team doesn't use that name since, technically, with callback functions, you provide the function's name, whereas in this case, they give you the name of the function that needs to be implemented. So then, what are these event handlers? They're functions that get called from the USB stack, usually from within a USB interrupt service routine. For example, if the USB bus is powered on, this is called a VBus on event. When this happens, one of the many things the stack will do is ask us if there's any code we want to run in response to this event. While ask isn't really the right way to put this, what they'll do is run the USB_VBus on event handler function. If you want something done, edit that function by adding your code to it. By the way, they provide you with an empty function in the USB app folder. Another example might be the USB suspend event. This function will get run if the USB host ends up suspending your device. Now, let's go ahead and look at using the USB. We've outlined this in 3 parts. The first part is planning your system. The old adage, plan first, applies here as well. The first thing you need to do is answer some questions, such as those shown here. Figuring out your needs is important because different classes provide different results. For example, the CDC Virtual COM port class provides bulk USB transfers. These usually result in higher transfer bandwidth, but you don't get any guaranteed bandwidth or latency. On the other hand, the HID human interface devices provides guarantees, but doesn't utilize the bulk transfer method, so their data rates won't be as high as the CDC can achieve. Once you've determined your system's needs, you can import the empty USB project and then run the descriptor tool to generate all of your interface's USB descriptors. With that done, you should actually have a running USB application. Although this is true, it's also true that it won't do anything other than connect properly to the host. Now, though, you're ready to add your own application's code to the program. In this next part, we looked at connecting and enumerating devices to a host. The process of connecting a USB device to a host is called enumeration. In fact, you may have seen a pop-up at some point in Windows that tells you it's enumerating a device that you plugged into its USB port. The USB connection state diagram is a 6-step procedure. On this slide, we show the first 3 states. 1. We always start out disconnected. When the cable is connected, the host applies power to the VBus signal of the USB cable, and that starts the connection process. 2. At this point, we move to the connected but not enumerated state. By the way, this is when the stack will call the VBus on event handle. Then, once we've called USB setup from our program, the stack will pull up the PUR resistor and tell the host we're ready to move onward. 3. We've reached the enumeration is in progress state. Finally, once enumerated, we move to state 4, where our bus is active. By the way, in response to achieving this state, the stack calls the enum complete event handler function. Basically, this is the active state where we do all of our communication. As long as the bus is active, we can use the send and receive functions that we spoke about a few minutes ago. If the host suspends your connection, you won't be able to transfer data, and potentially worse, you can only draw 200 milliamps from the USB bus versus the active power of 500 milliamps. Then again, we're talking about the msp430. 200 milliamps is more than enough for our processor, although I guess it depends what else you have running in your system. In any case, you may want to react to this change in state. You can do this by adding code to the suspend event handler function. As just a quick reminder, yes, you can affect the connection state. While you don't control the bus transfers, as only the host can do that, you can use the stacks function to connect, disconnect, start, stop, and even suspend your own connection. The third part, managing my app and transferring data. Once you've configured your application, via the descriptor tool, there's 3 ways you can write your code to interact with the USB port. We'll look at each of these over the next 3 slides. To get us started, we're going to look at the USB connection state function listed under the USB_API part of the stack. This is pointed to by number 1 on this slide. When we call the USB connected state function, we're asking the USB to tell us which state we're currently in. As it responds with one of 7 different values, it's handy to use this function within a case switch statement, as shown here. Although if you only cared about checking for a single state, you might prefer to use it as part of an if-else statement. In fact, more than just showing it here, this code is actually in the main.c file that's automatically added as part of the empty USB project. What's the advantage of using the connected state function? It makes it real easy to have your application respond to different USB connection states, as is often the case in USB-based applications. The disadvantage? It's constantly drawing power if this while loop is running all the time. Then again, if you're connected by a USB cable, you can be using their power, and then maybe you don't care as much about going to sleep. Another way we can interact with the USB stack is to add code to the event handlers. One big advantage of using these handlers is that because they're mostly kicked off by interrupts managed by the stack, they'll wake up your CPU if you put it into a low power mode. The disadvantage is that because they're run from an interrupt service routine, we don't want to do a lot of heavy processing in the event handlers. Take note of the last bullet on this slide, as it's quite handy. You can tell the stack to let you go back to low power mode or stay running based on the return value you set in the event handler. Bottom line, you can use the combination of events and the connection state function from our previous slide to manage how your application responds and uses the state of the USB bus. Last, but not least, we wanted to remind you of the construct functions that we spoke of earlier. Remember, we called them wrapper functions, for they often extended the data transfer calls found in the actual stack API. Of the 3 ways we've talked about interacting with the USB stack, the first 2 help us manage our code based on the USB's connection state. This third one, though, actually lets us transfer data to and from the host. And we finally reached the USB lab exercises. The USB lab exercises consist of running 3 examples. These give us a little experience with USB on the msp430, as well as some familiarity with the tools provided by TI. Then, Lab D asks us to start with the empty USB project and build an HID interface that communicates the push button state to the host. Between all the code provided for us in the empty project, as well as all the code we're reviewing through the first 3 examples, it should be pretty easy to get our program up and running.